I'm happy to have the opportunity to open this last session of this workshop. The first speaker is John Ball, who will speak on polycrystalline microstructures.
Okay, thank you, Peter. So I'm going to try and make some remarks aimed towards developing some kind of more rigorous theory for polycrystals, which is a bit ambitious since we don't really understand what goes on in single crystals properly, but I will do my best, and there's one or two remarks which I've developed under the deadline of giving a talk over the last couple of weeks, so there may be, of course, mistakes in them. I hope not. Okay, anyway, let's start. So what are polycrystals? Well, most alloys crystallize into polycrystals, that is, in different regions of the alloy, the orientation of the underlying crystal lattice is different, and the regions in which the underlying orientation is the same are called grains. So, for example, suppose we had a material which, above some temperature theta critical, was in a cubic austenitic phase. So this is drawn two-dimensionally. Of course, it's really three-dimensional, but you see in each grain the lattice has a different orientation. And what I'm interested in this talk is what microstructure arises in a polycrystal due to a martensitic phase transformation at this critical temperature, theta critical. So you reduce the temperature below theta critical, and then in martensitic phase transformations, the underlying lattice changes its shape. And it can change its shape in different ways, and they've all got to fit together, and that determines what the microstructure is. Now, martensitic phase transformations have no diffusion, or negligible diffusion, so there's no diffusion either within the grains or of the grain boundaries. So, of course, if you're at a higher temperature, grain boundaries can move due to diffusion. That's a very important thing to study, but we're working at a lower temperature than that. Actually, there's interesting effects that occur, interactions between grain boundary motion and microstructure, for example, connected with so-called annealing twins. And a lot of these issues of compatibility, I'm sure, apply in that sort of situation, but I know relatively little about it, and it's much more complicated because it couples both the difficult problem of grain boundary motion with the formation of microstructure. Okay, so the general aim then is to understand the microstructure morphology by taking seriously compatibility conditions both inside the grains and across the grain boundaries. And for this one needs, of course, an appropriate mathematical model, and I'll be taking nonlinear elasticity without interfacial energy, but you might well want to put interfacial energy in there. And then you need a description of the geometry of the grains. And then you need ways of applying compatibility, well, both in the grains, of course, but also at grain boundaries when the microstructure on either side may a priori be complex. So let me begin with trying to describe grain geometry. Actually, when you look at all the sort of mathematical work on polycrystals, people rarely say exactly what they're assuming about the geometry of the grain. So I'll try and say something which not very exciting, but to try and describe what the geometry might be. So we're going to consider a polycrystal that in a reference configuration occupies a bounded domain omega in Rn. N will be 2 or 3, but I'll just leave it as n. And it's composed of a finite number of disjoint grains omega j, so n of them, capital N of them, and each omega j is a bounded domain. So that omega is going to be the interior of the union of the closures of the grains, right? So here the closure is, of course, just omega j together with its boundary. Now, if you just assume that, then there are sort of pathological examples like the lakes of Wada, which are 3 bounded domains in the plane which have a common boundary. Now, we don't want to consider such pathologically shaped grains, so you need supplementary hypotheses on the boundaries of the omega j. And Unless otherwise stated, I'll assume that each omega j has a Lipschitz boundary. Now, of course, it would make no sense to suppose that the boundaries of each grain were smooth, because they have to come together, they have to meet, right? So they're going to have some kind of discontinuities in the slope of the boundary. So, but a Lipschitz boundary, which includes polyhedra, is a sort of pragmatic choice. Okay, now some topological information is encoded in the graph whose vertices are the grains, which we can label 1 to n, and then you have a choice as to what you do about what the edges of the graph are. So, so I'll suppose here, for example, that ij is an edge, so there's an edge joining I to j. If the grains omega I and omega j have a common boundary which has a part which has n-1 dimensional Hausdorff measure positive. So for example, if n is 3, that means that there's a portion of the common boundary which has positive area. Okay. Now if n equals 2, this kind of idea is used in the proof of the four-color theorem. I spent about an hour last night trying to find references for whether things like this are done in 3 dimensions without any success, but it's probably something is done in 3 dimensions. In 2 dimensions, it seems that does determine the topology of the grains. In 3 dimensions, I really don't know. And for example, you could let, for each grain I, you could let mi be the number of j's not equal to I for which ij is an edge. Right? We'll actually use that in a moment. So here's a picture of a polycrystal, written in 2D, of course. And so you see there's a difference between interior grains. Those are ones for which their boundary is contained in the union of other grains, and boundary grains. So the boundary grains here are in grey, and the interior grains are in white. Now, for example, A and B are interior grains, but they do touch the boundary. Okay. And then you can look at the set of triple points. These are the sets of points which belong to the intersection of the boundaries of 3 or more grains. Right? So something like this, for example, would be a triple point. So now a grain is convex if the line segment joining any 2 points in the grain lies in the grain. So here's 2 points, and here's the line segment joining them. It lies in the grain. So the grain in this picture, the grain A is convex, but the other ones in the picture are not. So you could ask what happens if all the grains are convex. Okay, so well, in that case, every interior grain is a convex polyhedron. It means it's the intersection of a finite number of open half spaces with at most mi faces. And this is sort of simple to prove, I think. So you take the j that have whose boundary intersects the boundary of omega I on a set of positive area. Those are 2 convex sets. You can separate them by a hyperplane. And on one side of the hyperplane is omega I, and on the other side is omega j. You take the intersection of those hyperplanes, you get a polyhedron, and you check that is in fact omega I. Okay. Of course, that's not the case at the boundary. So now then you can ask, well, how big is the set of triple points? So this is potentially useful because it's going to be easier to apply compatibility at part of the boundary which is just part of the boundary of 2 grains. It's more complicated if you're at a triple point. So you'd like to know that the set of triple points is in some sense smooth. Now in 2D, if each grain is the interior of a closed Jordan curve, so that's sort of weaker than saying that the boundary is Lipschitz, then there are at most 2 times n-2 triple points. And this is an example where the bound is sharp. Now in 3D, That's more complicated. I don't know whether there's a sort of counting argument like this. There might be, where you take different numbers of boundary components and so on. But you could also ask for some kinds of more quantitative information. So here's a partial result, not terribly satisfactory, but if under this weak condition that the omega j bar is a topological manifold with boundary, that means that any point of omega bar can be homeomorphically mapped on either onto a ball or onto a half ball. Then the set of triple points is nowhere dense in the union of the boundaries. Okay. So you'd like to maybe measure theoretic statements of that type as well, but I haven't managed to do that up to this point. Okay, now, so that's something about geometry. Of course, also we have the fact that in each of these grains there's a particular rotation of the lattice. That's another part of the geometry. So now we have to have a mathematical model for the energy. So first of all we do that for a single crystal. So this is the usual sort of setup. You have a reference configuration for your crystal. It's a single crystal now. It occupies omega. So there's just one grain, if you like. And then a deformation x maps to y of x. And then the total free energy for a single crystal, then you get by integrating a free energy density that depends on the deformation gradient and the temperature. So the deformation, this free energy density is defined for matrices in GL plus 3, that is real 3x3 matrices with positive determinant, so as to avoid reflection of the body and interpenetration of matter and so on. And theta is the temperature. We just regard it as a constant parameter. And in order to encode the phase transformation into the properties of that energy density, it's convenient to look at the set of matrices that minimize the free energy density at temperature theta. We'll call that K of theta. And we're going to work at a fixed temperature, so you can always suppose that in fact the minimum value is 0. So that's what later I'm going to be talking about zero energy microstructures. And I'm just going to be working for temperatures less than the critical temperature. And then we could assume that K of theta is the union of a finite number of martensitic energy wells. So martensite is the low temperature phase. Each one is given by SO3, that's rotations, times a positive definite symmetric matrix. And the rotations are there because of frame and difference of the energy. So for example, if you have a cubic to tetragonal transformation, so in the high theta bigger than theta c, the lattice is cubic, and then when you reduce the temperature, it can change shape to a tetragon, which is a brick-like object with two sides equal and one side different. And there are three possible ways in which you can do that. You get three different so-called variants of the martensite, and so the UI are given by these three diagonal matrices, and the two parameters eta1 and eta2 give you the dimensions of the box with respect to the original cubic box. So now let's look at zero energy microstructures for a single crystal. So now we're going to fix theta less than theta critical, and we'll drop the dependence on theta. So I'll just write it as psi of A, and K of theta I'll call K. And zero energy microstructures correspond to a gradient-Young measure with support in K almost everywhere. So the gradient-Young measure gives you the asymptotic distribution of the gradients near a particular point X. So here we're allowing infinitely fine microstructures that could be generated by, for example, minimizing sequences for the energy. And another way of trying to understand this is to look at the corresponding macroscopic deformation gradient. So these, if you like, you're looking at a length scale large enough so you don't see very fine oscillations in the deformation gradient. Instead, you see this macroscopic deformation gradient, and it's known that equivalent to this, you must have that the gradient of y at x, which is this 3x3 matrix, belongs to the so-called quasi-convex hull of this set K almost everywhere. And the quasi-convex hull you can either think of as the centers of masses of homogeneous, that means x-independent gradient Young measures whose support is contained in K, or another way, this is Svarak's definition, which is equivalent, it's the A such that psi of A is less than or equal to the maximum of psi over K for all quasi-convex psi. Now if you don't know what quasi-convexity is, it's the central convexity condition of the multidimensional calculus of variations. And although we know a lot more about it than we used to, we still know very little about it. And in particular, we don't know how to determine whether a particular function is quasi-convex or not. And so you see here, because this set KQC is really an object of experimental interest, it's handicapped by this fundamental mathematical difficulty that we face about quasi-convexity. Okay, now because of that, KQC is only known explicitly for the case of two energy wells, two variants. So and then you can take, if you use appropriate coordinates, K to be SO3 U1 unit SO3 U2, and you can take U1 to be diagonal A to 1, A to 2, A to 3, and U2 to be diagonal A to 2, A to 1, A to 3, so you keep the A to 3 in the same place and you swap the first two. And you can assume without loss of generality that A to 2 is bigger than A to 1. We don't want them to be equal. And A to 3 is bigger than 0. So this can occur for tetragonal to orthorhombic transformation, or for certain special orthorhombic to monoclinic transformations. And Dick James and I a long time ago calculated what KQC was, and it's the set of matrices F in GL plus 3 such that F transposed F has this form A, C, C, B, A to 3 squared, and A and B are positive, and this is the critical condition that A plus B plus twice the absolute value of C is less than or equal to A to 1 squared plus A to 2 squared, and then the determinant of this matrix has to be A to 1 squared, A to 2 squared. And we proved something else which is useful, that if the gradient of y of x belongs to KQC almost everywhere, then y is a plane strain. It's essentially two-dimensional. So y can be written as a rotation times y1 of x, y2 of x, which effectively or locally only depend on x1 and x2. Their three derivatives are 0, and a is a constant, and then we've got, in the third component, we've got a to 3 x3 plus a. Now let's turn to zero-energy microstructures for a polycrystal. So for a polycrystal, the total free energy is given by I of y is the integral of w of the gradient of y of x and x. So now w depends on x, but it depends on x in a simple way, that w of a of x is of c of a ri transpose. I put the transpose in here so I don't have to put it in elsewhere. So of c is the energy function for the single crystal for x in omega I. So Ri gives you how much the axes have been rotated in grain I. So if you're if x is in omega I, W is this. So if you like, it's a piecewise constant energy function which differs in these sets omega I. So that means that a zero energy microstructure corresponds to a gradient Young measure which for almost all x is supported in KRI, right, for almost every x in omega I. Or equivalently, it corresponds to a macroscopic deformation gradient y of x, which belongs to the quasi-convex hull of KRI, which is, in fact, the quasi-convex hull of K times Ri, okay, for almost every x in omega I. So now we ask whether there are possible zero-energy microstructures whether there are zero energy microstructures which are possible for any grain geometry and rotations. So these correspond to gradient Young measures such that the support of nu of x is contained in the intersection of all the sets Kr for R in SO3. So we're allowing the grains to have arbitrary rotations, right? And we want a deformation that's possible whatever the rotations in those grains are. Sorry. Or equivalently, it corresponds to macroscopic deformation gradients that satisfy that their gradient belongs to S, which is the intersection over all R of KQCR for all rotations R. Okay, so this set was essentially defined in papers of Bhattacharya and Cohn in the 1990s in connection with what they called the Taylor bound. So perhaps my interpretation is very, very slightly different, but it's essentially the same. Now what's interesting, well, a thing that's interesting about S is that it's isotropic. So QSR is S for all Q and R in SO3. So somehow, and that's because of course we've allowed any rotations of the grains. That's the rotation on the right, and of course frame indifferent gives you the rotations on the left. So now, since the only case that we know things explicitly are two wells, let's try and work out what happens for two wells. So here we go again, we're going to take these two wells with these conditions on the eta i's. And now, hopefully this is true, that S is empty in this case if eta 3 is not equal to the square root of eta 1, eta 2, and it's equal to this dilatation pre-multiplied by rotations if eta 3 is equal to the square root of eta 1, eta 2. So why is that? So since S is isotropic, you only have to determine the diagonal matrices that belong to S. And so suppose we've got this diagonal matrix D with the Di positive in S, then that means that for any R in SO3 there's going to be a corresponding A, B and C with these conditions. We're using this thing for the two-well problem such that this is equal to this. Now that's got a hold for all R. Now of course we can choose R's that permute such that this matrix here permutes these three numbers in any way we like. So that means that we have that all the di's squareds must be equal to eta 3 squared. Okay. So they're all equal to eta 3, and both sides of this equation are eta 3 squared the identity. So that means that C is 0 and A is equal to B, and thus eta 3 is the square root of eta 1, eta 2. That comes from the fact that the determinant has got to be eta 1 squared, eta 2 squared, so AB has got to equal eta 1 squared plus eta 2 squared, and then you have to check whether this inequality holds, but it does if this holds. Okay, so that completes the proof. So now, of course, this is predicated on asking for deformations that are going to be possible for any grain geometry, for any rotations. If you've got a particular polycrystal which has particular rotations in each of the grains, there may be other zero energy microstructures that correspond to that, okay, due to some kind of cooperation between the grains. Now let's consider something a little bit similar, but call it S2D. Now we're going to take the intersection of these sets, KQCR, but only over rotations which have axis E3. So now we're going to look for deformations that are going to be possible for any rotations of the grains which have axis E3. Right, so that turns the problem into essentially a two-dimensional problem, which is why I put 2D here. And here's the statement that F belongs to S2D if and only if you can write F is R, D, R tilde. R is any rotation. R tilde is a rotation which has axis E3, and D is a diagonal matrix which has one entry eta 3 and the other two v1, v2, and v1, v2 has got to equal eta 1, eta 2, and the absolute values of the vi's have to be less than equal to the square root of eta 1 squared plus eta 2 squared over 2. So this calculation was kind of started by Cohn and Niethammer in 2000, and it appears in the book of Doltzman. So Doltzman uses the right method, but in my opinion gets the wrong answer because he drops a 2 somewhere in the calculation, and that gives him much more complicated formulae. So I believe that this is the correct answer. Now there are non-trivial deformations which belong to this. For example, this one. So this is a sort of diagonal deformation gradient here, and I've got some now small thing which is some scalar depends only on x dot e perp. E perp is perpendicular to e. E and e perp are both in the x1, x2 plane. G prime, it has bounded gradient, and mod epsilon is sufficiently small. And such deformations non-trivially deform the grain boundaries. So I think that's interesting that you can have these zero energy microstructures which deform the grain boundaries, and it raises the question about what experimental evidence we have about the grain boundary deformations resulting from martensitic phase transformations. And I'll show you some other pictures in a bit later which may sort of expand on that thought. Now let's try and simplify things a bit and look for zero energy microstructures for a bicrystal. So I'm going to consider now just 2 grains, and what's more, I'm going to suppose that their structure is quite special. So we'll take the same energy wells as before, so 2 energy wells, exactly the same conditions, and now in grain 1 it's omega 1, so this is in R2 omega 1 crossed with 0d, so d is the thickness of this slab. So there we have the single crystal, so we need the support of nu x is contained in K almost everywhere. K is this. And then grain 2, it's rotated through a rotation with axis E3 through an angle alpha, and so the support has to be contained in KR alpha for almost everywhere in grain 2. And so let's ask the question, is it true that every zero energy microstructure is non-trivial? In other words, it's not a pure phase, a Dirac mass at a particular matrix belonging to the wells in each of the grains. Now, had it been that the interface between the grains was not vertical, so it would have the form x3 is g of x1, x2 on some patch, x1, x2, then you can't have a pure phase in one of the grains, because you'd have it, the grain would be linear on one side, and it would have to match a plane strain on the other side, and a simple calculation shows that is not possible. So actually, this case that I'm considering is the hardest case in this kind of context. And so the first result is that if the interface is planar, then whatever its normal, there's always a zero energy microstructure which has a pure phase in one of the grains. And therefore the interface has to be curved in order to show that the microstructure has to be non-trivial. So let's write the normal to the interface as n is cos theta sine theta 0, so that's the normal is in the x1, x2 plane, of course. And the second result says, well, let's take for simplicity the case alpha, the angle of rotation is pi by 4, then it's impossible to have a zero energy microstructure with a pure phase in one of the grains if the boundary between the grains contains a normal with theta in this set, D1, the blue set, and another normal with theta prime in the red set. Okay, all right. So this is, you might say, minimally interesting information, but nevertheless you have to work very hard to get it, and so we use this reduction to plane strains that reduces the problem to 2D and the characterization of the quasi-convex hull, but also we use a generalized Hadamard jump condition in 2D. So this is a jump condition which says if you have some kind of interface and you have some kind of Lipschitz map on one side and Lipschitz map on the other side, how are the gradients related? Okay, and we use such a jump condition to show that there has to be a rank 1 connection between the polyconvex hulls for each grain, which is the same as the quasi-convex hulls, and then there's long and very detailed calculations, and you can find the details in this paper which has actually appeared. Okay, now what about if you have more than 2 wells? Well, here's a very nice micrograph which comes from a very nice paper by Alt. This is barium titanate, which is a ceramic. It's cubic to tetragonal. Here you see a grain, and here you see immediately that it must be the case that the grain boundaries do deform in the martensitic phase transformation, because you see how the microstructures in the neighboring grain here are related somehow to the ones in the first grain. So presumably that happens because one of these grains crystallized first and the grain boundary deformed, and then when the neighboring grain crystallized, it took into account the fact that the shape of the boundary had changed, and so on. So let's consider a cubic to tetragonal transformation. So now I've got these 3 energy wells, and then S, this set of universally possible deformation gradients, contains a relatively open neighborhood of the dilatation which has the same dilatation as this. So if, like, I take the cube root of eta 1 squared eta 2 times SO3, it contains a relatively open neighborhood in the set of matrices whose determinant is eta 1 squared eta 2. Sorry, it disappeared. Okay, so and the proof is that S is isotropic, and by a paper of Doltzmann and Kirchheim, the quasi-convex hull of KQC contains a relatively open neighborhood of this multiple of the identity in D. So that's more or less exactly the proof. So what that tells you is that for cubic to tetragonal transformations, then this set of universal deformation gradients is non-trivial, and there'll be deformations in there which deform the grain boundaries. And in fact, if the austenite's cubic and the transformation strain is not a dilatation, then the quasi-convex hull contains a non-trivial set of tetragonal wells. So it's effectively in the work of Bhattacharya, and we wrote down details in this paper, so that S contains a relatively open neighborhood of this dilatation in this set D, the set of A, such that the determinant of A is the determinant of U. So, for example, you have a non-trivial S for cubic to orthorhombic transformations. Here is a sort of slightly related remark that there's no, so this is cubic to tetragonal, there's no homogeneous gradient Young measure which is supported on just 4 matrices in the cubic to tetragonal wells, and which on the boundary, if you like, or it's a gradient, it's a homogeneous gradient Young measure. Its center of mass, which you can think of as imposing boundary data, is given by that dilatation on the boundary. So now here's a picture again from Alt of a grain where, well, not exactly, but more or less, it seems that you have 4 deformation gradients. It's layers within layers, okay? And that's cubic to tetragonal. So the question is, what's this conflict with experiment? Is it because the deformation is not a dilatation on the boundary, or is it because we've ignored interfacial energy? So Alt makes a lot of very interesting heuristic comments about the effect of interfacial energy on these microstructures, and so there's a lot of interesting potential mathematical problems that one could look at there, I think. So another issue which we saw, and this is my last slide, saw in the work of Francesco, in the talk of Francesco Della Porta, is whether all microstructures, so I've defined what a zero energy microstructure is. It's such that the support of the mu of x is contained in KQC Ri, almost everyone omega I. But this microstructure has had to be obtained somehow from the austenite, right? So there has to be some kind of path in the space of microstructures which is sort of realizable in a physical sense. It takes you from the austenite to your microstructure. So maybe this imposes extra conditions on the microstructure. So, and he showed this beautiful micrograph of Tomonori Inamura, which forms part of the publicity of this program. And well, actually, he didn't show the neighboring grains, he just showed the middle one. So this is a grain, but now you see the neighboring grains, and you see that they're not exactly polygonal, but not so far from polygonal. So this is the alloy. It's cubic orthorhombic, middle eigenvalue 1, but I think not satisfying the cofactor conditions. And so the identity corresponds to the high temperature phase. Here are the 6 orthorhombic energy wells, schematically represented by circles. Well, they're like SO3, of course. And there's a rank 1 connection from the identity to each of these energy wells, exactly 2 rank 1 connections, actually. So there are exactly 12 matrices which are rank 1 connected to the identity. But these 12 matrices have no rank 1 connections between them. So the idea is that you started with the identity and each of these, which is the austenite, and each of these gradients here. So in this picture, more or less each color is one of these, or close to one of these gradients. So the idea is that each of these gradients at one point was in contact with the austenite, which is the identity. So there's all sorts of issues here, but I mean, for example, it could be that during the evolution, a piece of austenite got separated off from the rest and then rotated, in which case it wouldn't be right to put the identity there, but a rotation. So in any case, it would be interesting to calculate what the quasi-convex hull of these 12 matrices are. So they don't have any rank 1 connections, but they might have these T4 configurations in them. So my thought was that this is an experimental realization or experimental approximation to an exact gradient that takes 12 values without rank 1 connections. So we know that such deformations are theoretically possible. There are examples of Kirchheim and Price, so possibly this is what we're seeing here. But Francesco made the remark that apparently you cannot match the identity on the boundary here. So, but maybe you don't have to match the identity on the boundary. What you know about this, following his calculation, is that that this quasi-convex hull is contained in the set of matrices identity plus A tensor n, where A is perpendicular to n. Okay, but it seems to be the only easy information to extract. Okay, so I stop there.
Other questions? Yes, Claudio.
As far as I remember, the barium titanate is ferroelectric in the tetragonal form and not in the cubic. So I wonder if you apply an electric field and you break the thing into polycrystal, is there a possibility of directing the polycrystal in the direction of tetragonal or?
I pass on that, but maybe somebody else would could answer.
Is the example that you showed, the experimental example you showed, actually a good representation of the problems that arise in the martensite? Because you spoke, as you were describing the first...
You're talking about this particular picture or different?
No, the alt.
The alt one, yes.
You said, well, the grains are crystallized at different times, but the analogous problem for martensite would surely be that you have austenite grains, and then they all make a transformation to the martensitic state at the same time, roughly.
I don't think. Well, I mean, there'll be some kind of sequential.
But the grains are set down while it's in the austenite phase, so that those boundaries are established at that point.
The boundaries are established, and the boundaries don't move. That's right.
Right.
So it's just a matter of terminology. John said crystallized, but he meant transform.
Transform, yes.
Sorry.
Okay, thank you,
Yes.
thank you.
Okay, so they're transforming. So then to go, my actual question is that can you assume, I mean, you obviously don't want to do this, but can you assume, or could you assume that the boundaries are set and you have the transformations in them and the boundaries never actually deform until we come to...
Well, they can deform, but they don't diffuse. That's the, I think that's...
Do they deform during this transformation?
Well, that's the question. I think that the answer has to be that yes, they do. But of course, it's not so easy to get information about that. I mean, even this picture, you know, is not such a trivial thing. This is an interior grain.
Yes.
And in order to get this picture, he had to slice it with a hot wire and then, you know, retreat the surface because the hot wire, you know, destroyed things on the surface, and then do EBSD and then do some computer analysis in order to color the things and so on. So,
can I ask you another one?
yeah.
So when you're considering the compatibility between pairs of grains through a wall,
Yeah.
each grain is of course connected to lots of others, and that you make a choice in one, it's going to affect how these two make a choice over here. And I just wonder, in higher dimensions, like in 3D, it's surrounded by impossibly many grains. That actually, the answer is it shouldn't do anything at all.
So one little result which is sort of very intuitive, which I forgot to mention actually. I mean, so you could make some kind of generic hypothesis, right? So for example, you can ask, if I have a bunch of martensitic energy wells and I have another bunch but rotated by some r, is there a rank 1 connection between those energy wells? And generically, that's not true. You can't prove that. So that's a little thing that you could do, which uses some kind of generic argument about analyticity. But so maybe there's some way of proving better results under some generic hypothesis. I don't know.
How would your analysis change if you introduced a finite porosity?
No idea. But could you explain a bit more what you mean by the... So you mean vacancies? You're talking about vacancies?
No, not vacancies, but pores. That means space is not filled with grains anymore. You could have space.
Grains are missing.
They're missing grains.
Well, that would just be the... I mean, so that would just add some boundary grains, if you like.
Tiny missing grains.
Yeah, that would just add boundary grains near the pores, I suppose. But maybe you're asking a question about lots of pores. I'm not sure, but I'm not sure of sort of experimental situations where that arises. But maybe they.
Oh, indeed,
does.
they do.
Well, we could talk about that. That'd be interesting.
That picture from Ireland had some regions which didn't seem to be anything at all. Is that what you were thinking?
That's what I think.
Yes.
It was further back, right? This one, okay.
Yeah, the black one in the middle.
This. So is that a grain or
probably a pore?
Maybe it's a hole, yeah, or maybe it's I don't know.
And then lower down.
Lower down.
Yeah, down there, yeah. I don't know what that is. Yeah.
Very well. Let's thank Mike again.